Hello dear students, I welcome you all to the last edition of online class on mathematical reasoning. Okay, so yesterday I gave you some set of questions based on truth table. So that is one of the very important problems that you may see in your final exams. Okay, and today we are going to see another kind of problems that we are going to get in our final exams. Okay, so before doing the problems, we have to understand few things for the day. Okay, and the very same thing is the topic for the day. Okay, and the name of the topic is validity of statements. Now we have learned various kind of statements, simple statement and compound statements, and within compound statements we came across logical connectives like and, or, isn't it? Now let us see the validity of such kind of statements, and the first kind of statement is validity of and statement. So wherever you see and, you want to check whether the statement is valid or not, or you want to check whether the statement is true or not. Okay, and you know that whenever you see and you want to have overall statement to be true, then we must have both the component statement to be true, isn't it? Because if P and Q are T and T, then only P and Q will be T, isn't it? So component statement must be true in case of and statements. Okay, now we have got another is or statements. Okay, and in or statements we know that if any one of the statement is true, then the whole statement, the whole compound statement becomes your true, right? So that's why any of the component statements must be true. All right, now these are the simple things, okay, so which you won't see during your exam. You might see, but there is less chance for seeing these kind of statements. All right, but this, okay, this is the main thing that we have to learn in this particular chapter. Okay, so here we are going to talk about validity of if then statement. If then means conditional statements. Okay, now there are three techniques of proving some statement to be true. Okay, and the name of those techniques are direct method. We'll understand using problems. All right, so direct method, I am writing this as DM. Okay, next is contradiction method, this is CDM, and third one is contrapositive method. Now these three are for proving something, some theorems or some statements. All right, but sometimes they may say disprove that this happens. All right, so in such case, whenever you are asked to disprove or whenever you want to show something is false, that time you have to make use of something called counter examples in case of if then statements. Okay, now we'll understand these three one by one later on, and after this comes validity of biconditional statements, that is if and only if. Now if and only if is also like if then, isn't it? But this if then works only from the front, but if and only if work from backward as well. That means it is bidirectional, isn't it? So in if then, if and only if statements, there also will make use of the very same conditions, but we have to make the use of these twice. All right, because you are working front and back, so that's why you have to make use of these twice in case of biconditional statements. All right, so I want you to pause the video and note down the important points, that is these steps. Let's try and understand what is the meaning of these three methods as I said earlier. So consider the statement if then statement, that is P implies Q. Now what is the meaning of this? This means if P then Q, right? Okay, so please remember, whenever you see this P is always given to you. Okay, so that means what you need to prove? So you need to prove Q. All right, there are two statements here, and whichever is coming front, okay, so that means that is already given to you. Okay, and then Q, right? So this is the statement that needs to be proved. That's what we need to remember all the time. So direct method is nothing but it is simple. So it is, in this case given is P, okay, then we need to prove Q. Okay, somehow you just need to verify Q. So that is your direct method. Okay, we'll see a few problems, then you will definitely understand. Okay, so the next thing is contradiction method. Okay, so our aim is to prove Q, right? Okay, so what do is we'll assume that Q is false. Okay, so assume that Q is false. Okay, now if Q is false, then what happens? We have to work backwards. Okay, and we'll arrive at that point where we'll show that Q is also false. Alright, okay, so we'll assume that Q is false. Actually, we need to prove Q, but we'll take this opposite of Q. Alright, we'll assume that Q is false and we'll arrive at P. Okay, and we'll show that P is false. But what is happening here? P is given, that's why it has to be true, right? So that's why from there we come to the conclusion that our assumption that Q, whatever Q we took was false. Okay, whatever assumption we take, that assumption will be not valid. Alright, if it is valid, then what happened? We arrived at the contradiction. Okay, so that's why, that's how we use the contradiction method for proving if-then statement. Okay, so the last one is contrapositive. Now contrapositive and contradiction both are going to be similar. Okay, only the last step will be different, otherwise everything is going to be similar. All right, and we know that if P implies Q is the statement, its contrapositive is what? Its contrapositive is written as negation of Q implies negation of P, isn't it? Now see here, you are having now contrapositive, this one. Now what is the meaning of this? As I said, in this sign, whichever is coming front, that is always given. So in this case, this will be given to you. This will be given to you, and now you have to prove this. Okay, this has to be proved. So it's kind of this one only. Okay, because we started with Q, right? See, we started with Q and we are taking the false part of Q, and this is also false part of Q, isn't it? Negation Q means false part of Q, so that's why this is given to you and you have to arrive at negation of P. Alright, so these are the three different methods which are used for proving if-then statements. Okay, so we'll take few examples, then I'll give you some homeworks so that you'll be able to do them and you are going to be comfortable with that. Alright, so you may pause the video to note down. So let's see the first question for the day. So question says, show that the statement if x is a real number such that x cube plus 4x is equals to 0, then x is 0 is true by direct method, contradiction method and contrapositive method. Alright, so there are, okay, so there is one statement given which is in the format if then, right? So if this, then this. So that's why I can call this as P, right? And I can call this as Q. We know how to identify, or we know how to break the compound statement into its component statement. So this becomes my P and this is my Q. So basically I want to prove that P implies Q, right? And what did I say just now? I said that this means P is given to us, okay, and we want to prove Q, right? So that means our aim is to show that x is equals to 0. Alright, so let us begin with the direct method. Okay, so in direct method, what did I said? I said that P is given to us. That means given x is a real number such that this happens. Okay, so given x is a, or let me write x belongs to R. You know what is the meaning of this, right? This means x belongs to set of real numbers, that is x is a real number. Okay, and x cube plus 4x is equals to 0, right? Now can you see something common out here? Yes, x is common, right? So we have x is common. So if x is taken outside, we have here x square plus 4 equals to 0. Okay, now we know that x is a real number, right? Now if x is a real number, then its square is going to be always positive, right? So this is positive quantity now. Even if you take this as 0, then 0 plus 4, this is again 4, right? So 4 is again positive quantity. So if you take any value for x, then you will find that this full quantity is going to be positive. All right. Now if this is positive, then this quantity has to be how much? Because see, suppose this is positive, you may take any value. For example, if I take this to be 6, now 6 into something has to be 0. So what is the meaning of that? This means that this number has to be exactly 0. All right. So this means that x has to be equals to 0. Why? Because since x square plus 4 cannot be equals to 0. This is always positive. All right. So that's why, as I said, we need to prove that x equals to 0. So this is the direct method by which I proved that x is equals to 0. All right. So therefore x is 0. So that's what we need to prove out here. All right. So basically I showed that this happens in this particular case using direct method. All right. Okay, so we are done with direct method. Now let me show you how to work with contradiction method. All right. So next is contradiction method. So contradiction method. So as I said earlier, in contradiction method, what do? We take negation of this. Okay, we'll take that this is false. Now what is q? Q means x is equals to 0. Okay, so what is the negation of that, or the false part of that? The false part of this becomes x is not equals to 0. All right, and from there we'll arrive at the contradiction that this is equal to 0. All right, let's see how to do this. Now assume that x is not equals to 0. Okay, now if x is not equals to 0, that means if x is non-zero number, then what will happen to its cube? Will it be equals to 0? No, right? So clearly we have x cube will not be equals to 0, right? And okay, so x is not equals to 0 now. If I multiply that particular number by 4, that is 4x, will that be equals to 0 again? No, right? So again, we won't have 4x equals to 0, right? So that's why 4x is also not equals to 0. Okay, now x cube is also not equals to 0 and 4x is also not equals to 0. Then what will happen to their sum? So their sum will also not be equal to 0, right? So therefore x cube plus 4x. This is non-zero, this is also non-zero. I am adding them. So after adding them, I am finding that this will also not be equals to 0, right? So what is the meaning of this? We have p given to us, isn't it? This is happening, right? So this is always true. P is given, so that's why it is always true. And we took that this is false. And from there, we arrived at this. But this is against this, isn't it? Because it is given that x cube plus 4x must be equals to 0. But here I arrived at something ulta, that is x cube plus 4x is not equals to 0, right? Which is against our, okay, so as I said, this is called hypothesis and this is called conclusion, right? So which is against our hypothesis. Okay, so which is against our hypothesis. Therefore whatever assumption I made, that has to be wrong, isn't it? So our assumption was wrong, leading us to a contradiction, right? So therefore if x is not equal to 0 was our assumption which made this happen, that means we must have x must be equals to 0. So therefore x is equals to 0. So this is how we use contradiction. So let me repeat once again. So in contradiction, we have to take negation or just a false part of your conclusion, okay, and you have to work with that and arrive at P, okay, and you have to show that whatever conclusion you arrive, that is against your hypothesis. All right, so this is how we use contradiction method. All right, so you may pause the video to note down. I don't have space, so that we'll be able to see contrapositive method as well. Okay, so let's see our contrapositive method. So as you know, the contrapositive of this is what? This is negation of Q implies negation of P, right? So basically this is given to us now in this case. Okay, so given is negation Q. What is Q? Q is x equals to 0. Now what is negation Q? Negation Q means x is not equals to 0. Simple. All right, now as I said, this is going to be CPM is going to be similar to CDM. All right, so most of the steps will be same. Okay, so here clearly we say that x cube will not be 0 and 4x will also not be equal to 0. So therefore what do we have? This is x cube plus 4x will not be equal to 0. Yes. Now what is P? P is this one, right? So P says x cube plus 4x is equals to 0. Now what is negation P? Negation P is x cube plus 4x will not be equals to 0, right? And what is this? This is my negation P, right? So see, I started with negation Q. This is my negation Q, isn't it? And I arrived at negation P, isn't it? So therefore we have negation Q implies negation P, right? So therefore using contrapositive method we proved that P implies Q. All right, so you may pause the video to note down. So the next question says check whether the statement is true or not. Statement says if x and y are odd integers, then xy is an odd integer. Now in your mind just think of any two odd integers, for example 3 and 5, and find the product of 3 and 5. It is 15. Now 3 and 5 both are odd numbers, right? And their product, that is 15, is also odd integer, right? So that's why we can say that this is true. Okay, so if this is true, then we have to show it, right? We cannot take any example. So we can take examples only if we are disproving something, and that example is called counter example. Now whenever you are proving something, you cannot use example. That you have to take only in your mind for just testing, otherwise you cannot put it down in your paper. Okay, so we have got 3 techniques to prove such kind of statement, because this is if then statement, right? So we have direct method, we have contrapositive method, we have contradiction method. All right, so I'll just show you 2 methods, because you know that contradiction and contrapositive both are similar kind of proof techniques, right? So that's why I'll show you only two, that is direct method, and one will be contradiction method. All right, okay, so let us see what is P for me and let us see what is Q for me. Okay, so can I say that this is my P? Okay, so you have to mark what is your P and what is your Q. Without marking you cannot proceed. All right, okay, and this is my Q. Okay, now since the question is talking about odd integers, so let me give you a brief introduction about odd integers and even integers. Okay, so odd integers means 1, 3, 5, 7, right? And even means 2, 4, 6, 8, etc., right? Okay, so please remember general form of odd integers, okay, will be general form of odd integers will be equals to 2n plus 1. Please remember this. Okay, and general form of even integers will be always 2 into n. Okay, now put any value for n, for example 1, then 2n is 2, right? 2 into 1 is 2. which is even number. Put any value for n, that is for example 3. So 2 3s are 6. Again 6 is even number. So general form for even will be 2n, please remember that, and general form of odd integers will be 2n plus 1, because if you put any value for n, you will find this whole number will be always odd number. Alright, okay, so with this basic, let us begin. So it is given. Now we are proving using direct method. Okay, now in direct method we have P implies Q, that means given is P, right? So that is given is X and Y are odd integers. So if X and Y both are odd, then can I write therefore let X equals to 2m plus 1. Can I write this? Yes, put any value for m, you will find that this full thing becomes odd number, and we know that X is odd, and similarly Y will be equals to 2n plus 1. Alright, okay, so I have taken X and Y. So let us find their product, that is xy. Okay, so therefore xy will be equals to, okay, now we need to prove that xy is odd integer. That means I have to write in this way, plus 1. Okay, we have to write plus 1 separately, and we have to show that this will be even. See, this is even, 2m is even, 2n is also even. So whenever you add 1 to an even number, that becomes your odd number, right? So that's what we are going to do here. What is x? X is equals to 2m plus 1 into y. Y is 2n plus 1. Let us multiply. So after multiplication we see that 2m into 2n is 4mn plus 2m into 1 is 2m, right, plus 1 into 2n is 2n, plus 1 into 1 is 1. Alright, now we can see plus 1 in the same way, right, but this full thing has to be even number. We have to keep note of that as well. That means we have to take 2 common. So if I take 2 common from here, we have 2 into, from here we have 2mn plus from here m plus from here n, and we have got plus 1 separately, right? So let me write this as 2 into, now this is also one number, right, some number it is, so let me write this as 2k, alright, where k is equals to this full thing. Alright, so 2k plus 1, where k is equals to how much? 2mn plus m plus n. Now what is this? This is also odd number, isn't it? Right? If you see the format, this is also falling under the same category. So that's why from here we see that xy is odd integer, and that's what we wanted to prove, isn't it? Right? So this is how we prove this kind of sums using direct method. Alright, okay, so this is all about your direct method. Now let us go on to the contradiction method. Okay, now in contradiction method, what do? We take the false part of this, that means xy is an odd integer. This is given, this is there, this is what we need to prove. And what is the false part of it? Xy is not odd, that means xy is an even integer. Alright, so let me start with contradiction method. Okay, so this time you have to assume, so assume that xy is an even integer. Okay, so xy is an even integer, that's what is my assumption. Therefore, if xy is an even integer, then can I write this as xy equals to 2m or something like this? Yes, we will be able to write, as I said, that even numbers can be written as 2m or 2n, isn't it? Now, we took the assumption that xy is even, that is 2m, right? Now here one problem is, the product of two numbers will be even. We know that the product of two numbers will be even if any one of the number is even. For example, if this is 3, okay, then y has to be some even number, right? For the product to be even number, then any one of them has to be even, isn't it? So this means that either x is even or y is even or both, or sometimes both has to be even, but we know that both x and y are odd, isn't it? Are you understanding? I took the assumption that xy is even, that is 2m, but this means that the product of two numbers will be even only if one of the number is even. But here it is given in the hypothesis that both are odd integers, right? But okay, so either x is even or y is even or both, which is against our hypothesis, right? So therefore our assumption lead us to contradiction, making our assumption wrong, isn't it? Our assumption was wrong, so that's why we came to the contradiction, so making our assumption wrong. So therefore xy cannot be even, xy has to be odd integer itself. So xy is an odd integer. Alright, so that's what we need to prove here. Alright, so you will try contrapositive method in the same way. So you may pause the video to note down. Okay, so next question is, show that the following statement is true by CPM, that is contrapositive method. So the statement is, if x is an integer and x square is even, then x is also even. Alright, so that's what we need to prove. So as I said, in this case, that is if then statement, we need to first identify what is my p and what is my q. So if you see here, this is my p and whatever comes after then, that becomes my q. So this is my q, right? So we have to prove this using contrapositive method. So in contrapositive, what do? We have to show this, that is negation q implies negation p, right? So in such case, whatever comes front, that is always given to us, isn't it? So in this case, so my solution says given is negation p happens, that is x is even. What is the negation of this? X is odd, right? So x is odd integers. This is the negation of q. Alright, now if x is odd integers, so what is the meaning of this? This means that x can be written as 2n plus 1, right? And what is our aim? Our aim is to prove negation p. And what is p? P is x square is even, and what is negation of that? Negation of x square is even is x square is odd. Alright, so you need not pay attention to this. This is the main thing at last. Alright, so this is just to show that x is integer. You just need to remember that. Alright, fine. So we have to find now what is x square, and we need to prove that this x square is also what? X square is also odd integer. Alright, so from here we see that what is x square? X square is 2n plus 1 whole square, right? And we know that this is in the formula a plus b whole square, and we know that this can be written as x square is equal to a square plus 2ab plus b square. And what is a? A is 2n, so a square plus 2a, b is how much? B plus b square, right? Simplify this, so we have x square is equals to this 4n square plus this is 4n plus 1, right? Now our aim is to prove x square is odd. Odd means we have to keep plus 1, right? So we have plus 1 here, but we have to make this part, remaining part, in this format, right? So this can be written as 2 into, see here carefully, 2 into 2n square plus 2n plus 1. Yes. Now can I write this as something like k? Yes. So this can be written as 2k plus 1, where k is equals to how much? K is 2n square plus 2n. Now what is this? This is also odd number, right? So this means therefore x square is an odd integer, right? So therefore using contrapositive method we showed we showed that P implies Q, that is this statement is valid. Alright, so you may pause the video to note down. So the next question is on biconditional statement. As you can clearly see this sign out here, so this means the statement is biconditional and we need to show if x and y are positive or real numbers, then prove that this happens. That means this is my P, right? So this is my P and this is my Q. So you want to show P implies and implied by Q. Yes. Now what is the meaning of this? The meaning of this is P implies Q and other way around, that is Q implies P. Now so far we have seen, now this is also a conditional statement and this is also conditional statement, right? Okay, so these are conditional statement for you. Now you know the 3 ways of proving conditional statement. Alright, so during exam, whatever, see, suppose if this comes in your exam, then you can use any of those 3 methods. Alright, so this is not here, it is not mentioned that you have to use this particular technique, so you can use any technique out there. Alright, so let me use only one technique. So if you want to, then you can apply any other technique in order to prove the same. Alright, so I am going to do direct method here. Okay, so here it is given, so we need to prove. Okay, so let us, okay, so please mark this is my P and this is my Q. Alright, so let me prove this way, P implies Q. So I am proving P implies Q first. Okay, so P implies Q means P is given to us, right? So given is x is less than y, because this is my P, right? So P is given to us, where, now what is x and y? Where x and y are positive real numbers. Okay, so that's what is given to us. Now let us square both sides. All right, so you can think of any 2 positive numbers such that this happens. For example, 2 is less than 3. Okay, so let us square it. Now after squaring it, okay, so this is a real number, please remember. So after squaring, this becomes 4, right? And we have, okay, so after squaring this becomes 9. Now what will be the sign out here? Sign will still remain the same. Okay, now sometimes if you have something like this, for example, we know that -3 is less than -2. We know this. Alright, if I square here, what is the square of -3? It is 9. Yes, and if I square -2, what will the square? It is 4. But this time what will happen to the sign? Sign becomes this much, because 9 is greater than 4, isn't it? Right? So that's why I didn't put sign in the beginning itself. Alright, so you have to put sign later on after squaring. Alright, so squaring we get, so after squaring what do we get? Now as it is said that x and y are real numbers, so after squaring also the sign will not change. So after squaring also we will get x square is less than y square. Alright, so that's what is the meaning of this. Alright, so that's what we wanted to show here, right? So we have showed this part, that is P implies Q. Now let us work backward. So please remember this, all this has to be done in the rough part. You cannot show these numbers in your proof part. Alright, so let us prove the opposite part, that is Q implies P. Alright, so Q implies P I am showing you out here. Now what is the meaning of this? Q implies P means Q is given to you, and what is Q? Q is this, right? So given is x square is less than y square. Okay, where again x and y are what? They are positive real numbers. Okay, so again you will take some examples in your rough sheet, all right, and let us work with some perfect square number. For example, this is perfect square, x square is perfect square, right? So take the value of x to be something like 2, right? So we have 4 is less than 9. Both are perfect square, right? That means this can be written as 2 square is less than 3 square, which is in this format, right? Now if I take the square root, can I write this as 2 is less than 3? Taking square root? Yes. Okay, so you might be thinking the square root of 4 will be plus minus 2, right? Plus minus 2. And the square root of 9 is also plus minus 3. Okay, so if I take plus 2 plus 3, then is this valid? Yes, this is valid because x and y both are positive numbers. Yes. Okay, and if I take minus, so minus 2 is less than minus 3. Is this allowed? No, first and foremost they are negative, and this is also wrong because we know that minus 2 is greater than minus 3. All right, so you need to always write this. If you don't write this, then you will have problem out here, as I showed you, right? For example, you may write less than, but you may have greater than also after taking square root if the numbers are negative, right? So in order to make it the same sign, I have to mention that x and y both are positive, then only I'll be able to write less than. Otherwise, if I don't mention, then this also may come up. All right, so that's why I have mentioned at every step. Okay, so taking square root, we have okay, so we clearly have x is less than y. So that's what we wanted to prove, which is p, right? So that's what we proved here. All right, so using direct method, we have p is implying and implied by q. So that's what we wanted to prove here. So you may pause the video to note down. Okay, now this is the very famous problem in this particular chapter. So here you have to use contradiction method to prove that root 7 is irrational. So before I begin this problem, here you have to make use of two very important concepts. One is called co-prime. Okay, so co-prime means there is a pair of numbers, okay, where there is no common factor. For example, if I take 2 and 4, there is a common factor, that is 2, because here it is 2 and this 4 can be written as 2 into 2. So both contains 2 as common factor, right? For example, 3 and 21 or 6 or 21. Let me write 6 and 21. Now 6 is a multiple of 3, isn't it? 21 is also a multiple of 3. So that's why 6 and 21 both are having a factor 3. That means 3 is a common factor to both of them. Okay. Now if there are two numbers where there is no common factor, then such kind of numbers are called co-prime numbers. For example, 2 and 5. Is there any common factor between them? No. For example, 3 and 7. Is there any common factor in between them? No, right? So that's why such kind of numbers are called co-prime numbers. For example, 3 and 4 also, there is no common factor in between them. Such kind of numbers are known as co-prime numbers. Now the next thing that we have to learn is this special theorem. So this theorem says, if p is a prime number means, you know, right, 2, 3, 5, 7, right? So if p is a prime number and it divides a square, then p will divide a also. Okay, so these are the two things that you need to remember. All right. Okay, so let us begin. So it is given that root 7 is irrational. That's what we need to prove. But we are using contradiction. So in contradiction, what do? We will take the false part of whatever we need to prove, right? And we need to prove root 7 is irrational. So that's why we assume that. Okay, so assume that root 7 is rational. Now we introduced a new term, that is rational number. Now what do you mean by rational number? You say that a rational number is nothing but a fraction, right? For example, 2 by 5, 3 by 7, all these are rational numbers, isn't it? And irrational numbers are the numbers whose roots cannot be found. For example, this, right? Okay, so you said that root 7 is rational. Now if it is rational, then can I write this as, then can I write root 7 as a fraction like a by b, where a and b are co-prime. Now we have to make use of co-prime concept here. Okay, so there is no common factor in between them. Even if it is there, for example, 2 and 4, they are non-co-prime, right? So if I write this as 2 by 4, then what will be my answer? It will be 1 by 2, right? So 1 and 2, they are co-prime, isn't it? So that's why I have written co-prime here. All right. Okay, now here let me square it. Okay, so after squaring, what do I get? So after squaring, I'll get 7 equals to a square by b square, right? So from here we have, see here carefully, let me get this b square out here and let me take this 7 down. So we have a square divided by 7 equals to b square, right? Now see here, 7 is a prime number, isn't it? And this 7 is dividing a square, right? See here carefully, I'm going to make use of that theorem. So a square is being divided by a prime number. P divides a square. Now what is the meaning of this? This means that P has to divide a also, that is the square root of a square. So therefore, since 7 divides a square, then 7 divides what? Divides a also, right? Using that theorem. So divides a. Therefore, a by 7. That means if I divide a by 7, then I'll get some number. Let me assume k. So I am assuming that after dividing I am getting k. Okay. So from here, what is the value of a? So from here, a turns out to be 7 into k. That is 7k, right? Okay. I am erasing that part. So we have okay, so a is equals to 7k. So let us call this as equation 1. Let us call this as equation 1. So then 1 becomes, okay, so then 1 becomes, let us see what does it become. So instead of a, I am writing 7k. So this can be written as 7k whole square by 7 is equals to b square. Alright, and what is this? This 7 square is 49. 49 k square by 7 equals to b square, right? So from here, this and this gets cancelled, this is 7, right? So from here we see that b square by 7 is equals to, see here, this 7 is taken down, so b square by this is 7 is k square. Let me call this as equation 2. Now see here, 7 is a prime number. Again I am making use of the same theorem. Okay, so since 7 divides b square, then 7 must divide b as well, right? So 7 divides b as well. So therefore b by 7 must be equals to, for example, here I have written k, right? You can write L here, alright? So I am writing L. So from here, what is b? B is equals to 7 into L is 7L. Okay, now we have A equals to 7k, right? And B is equals to 7k. Now let me give it some number. Okay, so let me write this as 2. Let me write this as 3. Let me write this as 4. Okay, so from 2 and 4. Okay, so let us see what is happening in 2 and 4. So from 2, A is equals to 7k, and from 4, B is equals to 7L. Now what is the common factor here? We see that 7 is present with A and B as well, right? So common factor is 7, right, in between A and B. So from 2 and 4, the common factor between A and B is how much? It is 7. Now we know that A and B are co-prime, isn't it? Now what is the meaning of this? There is no common factor in between A and B, but here we found that A and B are having common factor equals to 7, which is a contradiction, right? For A and B being co-prime. So which is a contradiction for A and B being co-prime. Alright, so we arrived at the contradiction. Now at last you will write, hence, using contradiction, okay, so first you will write, our assumption was wrong. Hence, root 7 is not irrational, not rational, it has to be irrational. Alright, so that's how you will write at the end. So you may pause the video to note down. Okay, so next sum is, using contradiction method, prove that the sum of an irrational number and rational number is irrational number. So here also we have to use contradiction method, and our aim is to prove that the sum is irrational. So to prove using contradiction method, we have to take the false of the result that needs to be proved. So I need to prove here that the sum is irrational. I'll take the sum to be rational, please remember that. Alright, so assume that the sum of an irrational and rational and a rational is rational. So that's what is my assumption. Okay, so okay, so let me write the irrational number to be x. Okay, let me write this rational number to be y, and let me write the sum to be z. Alright, that is, whenever you are adding irrational number x with rational number y, then you are getting z, right? Okay, so which one is irrational out here? X is irrational, right? So let me take this y over there. So y is, we have x equals to z minus y. This is irrational, this is also, this is rational, z is rational, and y is also rational. So what will be the difference of rational numbers? Will this be irrational or rational? The difference will also always be rational, right? The difference between rational numbers will always be rational, isn't it? So here left hand side is irrational and right hand side is what? Right hand side is rational, which is just opposite. No, see, this is irrational, this is rational. So clearly left hand side is irrational and right hand side is rational, because the difference of rational numbers will be rational. That's what you have to write. Since difference of rationals is a rational number. Alright, okay, so which is not possible, right? So left hand side and right hand side both are not same, so this is not possible, right? So hence we arrived at the contradiction. Hence our assumption led us to contradiction, right? Contradiction. Therefore the sum of, okay, so you will write the same statement again. Okay, hence proved. So you may pause the video to note down. Okay, so let's see the last problem for the day, that is the usage of counter example. So as I said in the beginning, counter examples will be used in the place where you have to disprove something or you have to show that something is false. For example, here it is said that show that the statement, that is the statement is, for any real numbers a and b, a square is equals to b square implies a equals to b is not true. Is not true means is false, by giving counter example. So basically here this is my p, yes, and this is my q. So p implies q is false, so that's what we need to prove here, okay, using counter example, right? So given is real, a and b are real numbers, right? So given is, so this is my solution. So given is a and b are real numbers. Now since this is counter example, now you can choose any values for a and b. All right, okay, so we have a square is equals to b square. All right, now a square is equals to b square means there are two numbers whose square are equal. For example, we know that -2 and 2. Now what is the square of -2? It is -2 square is 4 is equals to 2 square. 2 square is also 4, right? So this is true, right? That is p is true, but -2 is not equals to 2, isn't it? So -2 is negative and 2 is positive, so they cannot be equal to each other, which is against this, right? See, a square is equals to b square, this is fine, all right, but a and b, they are not equal, whereas here it is showed that they are equal, right? So this is how we make use of counter example. All right, so using above counter example, p implies q is false, right? So that's what we showed here. So you may pause the video to note down, and your homework from this particular topic is given out here. So you will try this, and this is your, again, if and only if, that is biconditional statement. So use any of the three techniques, or you can try all the three techniques, that is direct method, contrapositive method and contradiction method, in order to prove this particular topic. All right, so with this we close this chapter. Okay, you please go through the solved examples as I said in the beginning, and see how the sums are done in solved examples as well. All right, so with this we close for the day. Thank you very much. So you may pause the video to note down.